Background. This section presents the background knowledge required for the design and implementation of the new cross-layer security scheme. It involves a review of the different techniques used in the development of the new security scheme. The multi-level convolutional cryptosystem constitutes the second stage of implementation at the physical layer. It receives integers from the RNS implemented at the first stage. The multi-level cryptosystem is implemented using subband coding and nonlinear convolutional cryptosystem. The integers from the RNS block are split into different levels of decomposition based on subband coding. Subband coding is implemented using integer wavelet lifting scheme. It is shown in that, a judicious choice of filter banks could result into an integer transform despite the fact that, wavelet transform is an approximation process. A 4-tapped OpG's polyphase matrix, which results into integer transforms, is given as follows. Where H and G are filter coefficients with suffix E and O denoting even and odd coefficients. The factorization of the polyphase matrix is as follows. 2. Forms the basis of integer to integer wavelet transform, which in effect is progressive transmission. The factored coefficients H1 equals -3, H2 equals 34, H3 equals 3 minus 24, H4 equals 3 plus 12, H5 equals 3 minus 12 are used to compute the approximate and detail sequences. In such transmission, the original data is split into two portions, namely approximate and detail sequences. The detail sequence is transmitted while the approximate sequence is further split into two halves. The process is repeated until the final data point. Using 2, the approximate, and in the detail, DN sequences could be computed as follows. Where N and DN are the approximation and detail sequences of wavelet coefficients of the nth sample. The subsequent transmissions are fed into the nonlinear convolutional coding block as depicted in for the first level kth detail and approximation sequences. The processing blocks, Ps, shown in the figure depicts the computations of 3. Synopsis for the computation of the kth coefficients for the first and second levels of decomposition. The final decomposition level, which comprises one data point, will give one approximation coefficient and one detail coefficient. At the destination, the inverse wavelet transform is performed to obtain the successive approximation sequences. 3. Is used to perform the inverse transform by reversing the operations for the forward transform and flipping signs. The process starts with the approximation and detail coefficients A0 and D0 respectively obtained at the final decomposition level of the forward transform. The first stage of the inverse transform is shown in the first stage of the inverse transform. The 2 symbol represents upsampling by 2, which means that zeros are inserted between samples while H2 and H3 are the filter coefficients used in 3. A major advantage of symmetric cryptography is the ability of composing primitives to produce stronger ciphers, although on their own the primitives will be weak. Hence, the vulnerable convolutional code block will be cascaded into different stages using the product ciphers obtained from the S-box and P-box to form a nonlinear convolutional cryptosystem. Key generation. The specifications of the private keys used in the implementation of the cascaded convolutional cryptosystem are as follows. States of each transducer or convolutional code block in the cascade given by the contents of the submatrices in the generator matrix. The transition functions. These are mappings used to compare the input bits in present state and switches to the appropriate next state. N-bit S-boxes. They are used to shuffle the output bits. N-bit P-boxes. They are used for the different permutations per level of decomposition. Key generation. The specifications of the private keys used in the implementation of the cascaded convolutional cryptosystem are as follows. States of each transducer or convolutional code block in the cascade given by the contents of the submatrices in the generator matrix. The transition functions. These are mappings used to compare the input bits in present state and switches to the appropriate next state. N-bit S-boxes. They are used to shuffle the output bits. N-bit P-boxes. They are used for the different permutations per level of decomposition. For illustrative purposes, N8, 2, convolutional encoder will be considered to demonstrate the keys generation process. For an 8x8 matrix, there are at least 216 ways or keys in which the connections of a register to the modulo 2 adder could be made. A possible key which gives the contents of the 8 times 8 matrix are shown in. For the generator matrix is used to specify the following set of 8 vectors. x7 equals a17 a37, x6 equals a17 a16 a36, x5 equals a15 a35 a36, x4 equals a14 a34 a35, x3 equals a13 a33 a34, x2 equals a12 a32 a33, x1 equals a11 a31, x0 equals a10 a30. It should be recalled that, for an N-K-L convolutional encoder, each vector has LK dimensions and contains the connections of the encoder to the modulo 2 adder. The structure of the 8-8-2 convolutional encoder is shown in with A2, A3 representing the registers M11, M21 while A1 represents the input data. Structure of an 8-8-2 convolutional encoder. For an 8,8,2 convolutional code, there are 28 equals 256 mappings or keys. There are 2 sets of transition functions denoted as F1 for the 2 possible states. For example, a transition function that compares input data to state 1 and remains in state 1 is given as follows. N5, if the input data is any of the sequences, the present state of the transducer which is state 1 is retained. A transition function that compares input data to state 1 and switches to state 2 is given as follows. N6, if the input data is any of the sequences, the present state of the transducer which is state 1 is changed to state 2. At the destination, the transition functions are similar to those for the encoder at the source but change roles. The transition functions are very critical in the implementation of convolutional cryptosystems since it accounts for its dynamic nature, hence an increase in security level. For an 8,8,2 convolutional code, using 2-bit shuffling boxes, there are 16 S boxes or keys. For higher in-bit shuffling boxes, the number of keys increases, for example 8-bit shuffling boxes will give 28 keys. The 4 2-bit S boxes used to illustrate the scheme are shown in Table 1. Given an 8-bit data sequence as, the lookup S box, sub 1, 1 is used to shuffle the first pair of bits, sub 1, 2 is used to shuffle the second pair, sub 1, 3 is used to shuffle the third pair, and sub 1, 4 is used to shuffle the last pair. 2-bit shuffle lookup table. The interconnections between inputs and outputs are implemented using a permutation set lookup table. For an 8,8,2 code, the 808 inputs and outputs could be permuted or interconnected in at least 77 equals 823,543 ways. A permissible permutation is shown in Table 2. Input-output interconnect lookup table for encoder. After the specification of the keys, the vulnerable convolutional code block will be cascaded into different stages using the product ciphers obtained from the S-box and P-box. Using 2 stages, a nonlinear, 2 cascaded is as shown in. Initial structure of the cascade before encoding. N, sub 1, 1, sub 1, 2, sub 1, 3 and sub 1, 4 are S boxes used for pairwise bit shuffling and the input vector to the first transducer. X7, X6, X5, X4, X3, X2, X1, X0, is the output set from the subband encoding block while the output vector, Y7, Y6, Y5, Y4, Y3, Y2, Y1, Y0, is the ciphertext from the second transducer stage. It is worth noting that the security level could be greatly increased by increasing the number of stages to be cascaded. The residue number system uses the Chinese remainder theorem, CRT, to compute unknown values from the remainders left or residues when unknown values are divided by known numbers. The modular Chinese remainder theorem states that assume M1, M2, Mn are positive integers, relatively prime pairs, me, mk, equals 1 if I hash k. Let b1, b2, bn, be arbitrary integers, then the system of simultaneous linear congruence. has exactly one solution modulo the product M1, M2, Mn. The solution to the simultaneous linear congruence is formally given as where Mj equals Mgen equals J equals 1 in Mj. 8. Establishes the uniqueness of the solution. In this research, the integers Tj equals Xjmj, often referred to as the multiplicative inverses of Mj, are computed a priori by solving the linear congruence in 7. In other words, if Mj equals M/Mj, then the multiplicative inverses, Tj, are computed by solving the congruence Tj Mj equals 1, mod Mj. Key creation. Choose secrete primes P and Q and compute M equals PQ. Choose encryption exponent, E. Compute D-satisfying ED1 mod, P, 1. Q, 1. Public key, M, E, and private key, D. Security services achieved using RSA cryptography are authentication and non-repudiation based on digital signatures and confidentiality based on encryption.